we are going to cover following topics. So let's begin with the first one. AI concepts. AI is the science of making computers think and act like humans. Machine learning, a subset of AI, helps systems learn from data and make predictions without being explicitly programmed. Deep learning takes it further, using neural networks to automatically learn complex patterns. It powers technologies like computer vision, speech recognition, and natural language processing. Machine learning. Machine learning is a technology that enables computers to learn from experience or past data and therefore become adept at predicting outcomes. So, in machine learning, historical data is fed into algorithms that analyze patterns and relationships. The result is a trained machine learning model, a program that can recognize similar patterns and make predictions on new data. Here's a concrete example. Our training data is a large dataset with features or columns like longitude, latitude, humidity, temperature, and whether it will rain or not. This data might be of last many years, therefore useful for training our model. Our machine learning process learns from this data. In other words, it figures out whether for a certain combination of values of the feature set, will rain would be true or false. For example, when temperature is low and humidity is high, will rain would be true. In general, larger the training dataset, better the learning, therefore more accurate the prediction. Here's what a typical machine learning workflow looks like. Historical data is first cleaned, whereby records with incomplete or missing data, duplicate records are removed, and inconsistent or bad formatting is corrected. Next, data is prepared. Here it may be split into training and test data. Post that, machine learning program processes the training data and creates a machine learning model, which is then evaluated using test data. The results are examined to tune the machine learning process further. Machine learning algorithms. Supervised learning. Here the model learns from labeled data. Here's an example of supervised learning. Input dataset has clearly labeled images of apples and mangoes. Our machine learning process learns from this and creates our machine learning model. Therefore, when a new mango image is fed to the model, it is able to identify it as mango correctly. Unsupervised learning. Here the model finds patterns in unlabeled data. Here our input data consists of a bunch of unlabeled shapes. Our machine learning process tries to find patterns in this data and successfully identifies similar shapes. So here we can see that unsupervised learning is useful in finding data clusters in input data. Reinforcement learning. Model learns through trial and error. Supervised learning algorithms. Linear regression predicts a continuous value based on input features. Example use case, predicting salary based on years of experience. In a graph form, it is about finding a best fit line to represent relationship between two variables. Logistic regression is used for binary classification. An example use case would be classifying emails as work or personal. Decision trees, a flowchart like tree structure to make decisions. Example use case, customer buying decision. Let's say we want to predict whether someone will buy a product based on their age and income using a decision tree. We can use a decision tree for this. Support vector machines finds the optimal boundary for classification. Example use case, image classification. The decision boundary is a hyperplane that separates different classes in the feature space used to distinguish between classes in a classification problem. The closest points from each class to the decision boundary are called support vectors. The margin is determined by the distance of the support vectors to the hyperplane. The decision boundary depends directly on the support vectors. If they change, the boundary changes as well. So support vectors are data points that sit at the edge of the margin. Naive Bayes is used for classification tasks. It applies Bayes' theorem to calculate the probability of different class labels based on the features of the data, assuming that the features are conditionally independent. Imagine you want to classify emails as spam or not spam. You use naive Bayes to calculate the probability of an email being spam based on words it contains. K nearest neighbor or KNN classifies new data points by finding the K closest points in the training data and assigning the most common label among them to the new point. It is mainly used for classifications and sometimes regression. So K represents the number of closest data points or neighbors to include. In this case, K is 3. So 3 closest data points are considered, and the most common label amongst these 3 data points is assigned to the new data point, or it is simply the average of its K nearest neighbors. Here's an example where value of K is 5. So in this example, the new data point in red is likely a fish because that's the majority among 5 nearest neighbors. And here's a regression example. The value of new data point for a K value 3 is average of 3 nearest neighbors. So that is average of 14, 10 and 6, which is 10. Let's look at unsupervised learning algorithms now. K means clustering. Groups data points into clusters based on similarity. Example use case, market segmentation in retail. And here are some data points. And this is how we have grouped them. K is a hyperparameter and stands for number of clusters that we are looking for. Here's a visualization of K-means clustering. Points are scattered across the screen. Centroids start in random positions and move iteratively towards their cluster centers. Dimensionality reduction. Reduce the number of features or dimensions in a dataset while preserving as much of the relevant information as possible. Dimensionality reduction is useful for simplifying models, reducing computation time, visualizing high-dimensional data, and minimizing the risk of overfitting. Now, there are two main types of dimensionality reduction techniques: feature selection, that is keeping only the most important features, and feature extraction, that is creating new features from existing ones. And here's a quick example where we remove redundant features. Principal component analysis. Here we reduce data dimensionality while preserving variance. Example use case, reducing features for image data. Let's learn about reinforcement learning algorithms. Q-learning, a model-free algorithm that learns the value of actions. Example use case, game AI, such as training agents in video games. Q-learning is a model-free algorithm where the agent learns a value that is Q value for each action in each state. It updates the Q values based on rewards received and aims to learn an optimal action value function. Use cases: grid world tasks, robotics, simple games. Deep Q networks combines Q learning with deep learning for complex environments. Example use case: robotics and autonomous driving. Deep Q network combines Q learning with deep neural networks, enabling the agent to approximate Q values for large and continuous state spaces. Use case: video games, robotic control, and complex environments. Now that we have covered supervised, unsupervised, and reinforcement learning algorithms, let's look at ensemble methods, where we combine multiple models to improve accuracy. Random forest uses multiple decision trees to make predictions. Example use case: medical diagnosis. It is an ensemble method that builds multiple decision trees using random subsets of data and features. For classification, it uses majority voting across trees, and for regression, it averages their predictions. This randomness reduces overfitting and improves accuracy. Gradient boosting sequentially corrects errors of previous models. Example use case: predicting customer churn. An ensemble technique that builds decision trees sequentially, with each tree correcting the errors of the previous ones. It optimizes predictions by minimizing a loss function using gradient descent. The final model is weighted sum of all trees, making it powerful for both classification and regression. XGBoost is a high-performance implementation of gradient boosting that uses decision trees. It optimizes speed and accuracy with features like parallel processing, regularization, to prevent overfitting and efficient handling of sparse data, making it ideal for large-scale tasks. Stacking combines multiple heterogeneous base models using a meta-model to improve overall prediction accuracy by learning how to best aggregate their predictions. Using diverse models reduces bias and variance. It can often outperform single models and is effective in cases where no single model performs the best, However, this can be computationally expensive. Neural networks. In simple terms, neural networks are computer programs or systems inspired by the way our brains work. They learn and make decisions from data, much like how humans learn from experience. A neural network is made up of neurons, layers, weighted connections, activation functions, and so on. Let's simplify that. Neurons are the basic building blocks of a neural network. You can think of them as mathematical functions that processes input data and produces an output. They are connected to other neurons through connections. Each connection has an associated weight that determines the strength of the connection. During training, these weights are adjusted to optimize the network's performance. A layer consists of a set of neurons and performs specific operations on the input data. They are one of the fundamental building blocks of neural networks. There are input and output layers at the edges, and the layers in between are called hidden layers. Each layer plays a specific role in transforming and extracting features from the data. A model refers to the overall architecture or structure of the network. It defines how the layers and neurons are organized and connected. What exactly does a neuron do? Let's understand what goes on inside a neuron. Assume x1, x2 and x3 are inputs to the neuron, which are simply numerical values, and w1, w2 and w3 are weights for each of the corresponding input connections. Every input is multiplied with its corresponding weight, and all the resulting weighted inputs are summed up, and a bias is added to it. The result is passed to an activation function which spits out the output for that neuron. Next obvious question is, how are weights, bias and activation function chosen? Both weights and bias are parameters that will be tuned during the training so that the neural network gives us accurate results. The primary role of the activation function is to transform the value given to it in a suitable manner for the next layer or the final output. It could be as simple as converting negative values to 0 and positive values to 1. Types of activation functions. There are many kinds of activation functions, like ReLU that replaces negative values with 0, sigmoid squashes input values to the range of 0 to 1, softmax normalizes input values into a probability distribution over multiple classes, binary step outputs 0 for values below a certain threshold and 1 for values above it. The choice of activation function in the hidden layer depends on the network type. So for a convolutional neural network, you may choose ReLU activation function, and for a recurrent neural network, sigmoid activation. And in case of the output layer, you would choose an activation function based on problem type. So for binary classification, sigmoid, and for multiclass, softmax. Types of neural networks. Depending on their architecture, neural networks could be of one of the following types: feed-forward, convolutional, recurrent, autoencoder, and so on, each designed to solve a certain problem type. The feed-forward neural network is the simplest type, made up of input, hidden, and output layers with information flowing in one direction. It's commonly used for tasks such as classification and regression. They are versatile. They can be trained for classification tasks, spam detection, or regression tasks like predicting house prices based on features. Convolutional neural networks are designed for processing grid-like data such as images and videos. They are commonly used in object detection, image classification, and image generation tasks. While CNNs primarily focus on images and videos, they can also be applied to other grid-like data structures like audio signals represented as spectrograms. Recurrent neural networks or RNNs are suitable for sequential data where the order of elements matters, such as time series, text, and speech. Here you can see the same recurrent layer in 3 time steps, T1, T2, and T3. Output from first time step is passed as an additional input in the next time step. In general, this can be represented as shown. Note the computation equation and how it is different from the one we have seen before. Autoencoders are used for unsupervised learning and feature extraction. They are made up of an encoder that maps input data to a lower dimensional latent space and a decoder that reconstructs the original data from the latent representation. So autoencoders are useful because they don't require labeled data for training. They learn by trying to reconstruct the input data itself. Autoencoders are used in denoising, anomaly detection, and dimensionality reduction. So that was a quick overview of neural networks, maths and statistics. So is math really a prerequisite to understand AI? For beginners, no. They should prioritize building stuff. It's counterproductive to get bogged down memorizing formulas. Instead, focus on hands-on activities, creating projects, training straightforward models, and exploring various datasets. What about industry practitioners? It's not a barrier. You can build functional models without knowing every single underlying equation, especially when starting out. Powerful libraries like NumPy and TensorFlow handle the intricate calculations for you. However, for research and innovation, it is absolutely critical. A deep theoretical grasp of mathematics is fundamental here. So what math should you prioritize? Linear algebra, basic calculus, stats, and probability. In linear algebra, matrices and vectors. This is how data is structured and manipulated. For example, adding, multiplying, calculating dot products. In basic calculus, derivatives and gradients. These describe rates of change. Gradients are the engine behind optimization methods like gradient descent. Optimization basics, concepts like finding minimum points on a curve and understanding its shape. In statistics and probability, distributions. Familiarize yourself with common data patterns, example, normal, binomial, uniform. Variance and covariance, crucial for understanding data spread, relationships between variables, and selecting relevant features. Maximum likelihood estimation, a method for figuring out best parameters for your models, like in logistic regression. Bayes theorem, a cornerstone of probabilistic reasoning used in algorithms like naive Bayes. So math serves as an enabling tool for your success. It should never be an obstacle to simply begin your journey. Gen AI. Generative AI refers to AI systems capable of creating new content such as text, images, audio, or code. It learns from large datasets and generates content. Here are some key Gen AI architectures: large language models, diffusion models, generative adversarial networks, variational autoencoders. We will go deeper into large language models soon. It forms the backbone of many Gen AI applications. Some examples of Gen AI applications or use cases are text, image, video and music, code generation, drug discovery and research. Large language models. In the AI landscape, large language models are at the cross-section of natural language processing, that is NLP, and deep learning. So what can LLMs do? They can generate text in natural or human languages like English, Spanish, French, etc. A large language model is a type of neural network which is very large, with millions of neurons and billions of connections between them, with each connection having a weight. LLMs are based on transformer neural network architecture. Transformers may use encoder-decoder setup. The encoder produces contextual embeddings for each input token, and the decoder generates the output sequence. Some models are encoder only or decoder only, depending on the task. They use the attention mechanism to weigh the importance of each token in a sequence, allowing the model to capture relationships between all tokens efficiently. Transformers process input tokens in parallel while still being aware of their sequence using positional encoding. This allows it to deal with relation between tokens using attention mechanism, and overall, this parallelization speeds up processing. Without the attention mechanism, the word bat in the sentence, "the bat flew out of the cave," might be interpreted as a sports equipment. The attention mechanism allows the model to consider the entire sentence for context and correctly identify that bat refers to a mammal. Vision language models. How do models understand images? In a LLM, you feed a text input and get a text response. Now, what if you have an image as an input? Standard LLMs cannot process that. This is where vision language models or VLMs come in. VLMs are multimodal, that is, they can take in text and images, interpret them, and generate a text response. So, for example, they can describe an image fed to it or extract text in it. But how do they do this? To understand this, let us begin with text input to a LLM. Text is converted into tokens before LLM can process them. In case of images, the input needs to be converted to similar tokens before LLM can understand them. And that's where vision encoder comes into play. It processes images as high dimensional numerical data and outputs a feature vector, which is a structured representation of image content. Next, these feature vectors are converted into image tokens by projector so that LLM can understand them. So now we have text tokens and image tokens both existing in the same latent space. LLM can process them regardless of whether they originated from text or image, resulting in a text-based response from the model. So a vision language model extends the idea of a large language model by adding a vision encoder and a projector. Retrieval augmented generation. Let's first understand the problem we are trying to solve. If we ask this question to a large language model, what is the revenue of a company XYZ this year? We are likely to get a response, sorry, I do not have this information. Now, although this information may indeed be available in many proprietary or public databases, the LLM does not have it because it has not been trained on it. Here's another question a business user may ask. Did we sell any mountain bikes last quarter? LLM cannot answer this question. It simply does not have this information. Therefore, our goal is to augment LLM so that it can respond with information that it has not yet been trained on. How can we do that? At a high level, here's how large language models are used. User question is sent as a prompt to a LLM and it returns a response. This works well, but with certain limitations. And the limitations are LLM knows only what it has been trained on and has a training cutoff date. Training LLMs continuously on latest real-time data is expensive and not always viable. LLMs do not have access to your proprietary or enterprise data. So, how do we address this? We can use what is known as retrieval augmented generation technique. Here, proprietary data is converted to vector embeddings by an embedding model and stored in a vector database. Based on user question, relevant data is first retrieved from the vector database and then a prompt is created which is made up of the original user question and the retrieved contextual data. This prompt is then sent to LLM to generate a response. With this technique, LLM successfully generates a relevant contextual response using proprietary data. So, any data, for example our proprietary data that we want to refer to, should first be saved as vector embeddings in a vector database. A vector database indexes and stores vector embeddings for fast retrieval and similarity search by programs. It is important to understand vector embeddings here, which is how the data is stored in a vector database. Vector embeddings are a type of feature representation of complex, high-dimensional data in lower-dimensional vectors. Our embedding model helps us do this conversion. You can think of vector embeddings as a form of compression, a way of capturing the essence of an object in a format that machine can work with. With respect to languages, embeddings enable us to quantify the semantic similarity between words or sentences, which helps with retrieving the most relevant data for the user question. So by now you would understand that retrieval augmented generation happens in two stages, retrieval and generation. The retrieval stage uses a separate model to search through a database of pre-compiled vector embeddings based on the user query to find most relevant information. The generation stage then takes the original query and the retrieved information and sends it to a LLM to generate a response. So, in conclusion, retrieval augmented generation uses this two-step process to generate responses that span a larger context window than traditional large language models. Where could you use this? Imagine using this within your enterprise to answer queries from your enterprise data. Agents. What are AI agents? And why do we need them? Here is a large language model. We send it a prompt and it responds. However, it cannot perform actions or in other words get things done, and its knowledge is limited to what it was trained on in the past. Let's add an orchestrator or an agent in between so that we send our queries to the agent instead of LLM, and add tools that can perform actions. Now our agent has access to both LLM and tools. LLM can do planning and reasoning while tools can perform actions. Tools can be of many types, like those that can invoke APIs or fetch data from a data source and so on. For example, weather tool can be invoked over REST and its interface is defined by an open API schema. Similarly, a data source can be queried to extract necessary information. We also need memory to enhance the capability of the agent. So let's add that. Now our agent can remember things. We can use both short and long-term memory here. We must have a way to instruct the agent. So let's add a prompt template, which is nothing but a bunch of instructions. That's our overall agent architecture. This should give you a good idea of key components that an agent works with. The central agent block can also be called as agent core or simply orchestrator. We will just call it agent for simplicity. Note that it is the advanced prompting techniques with instructions that enable LLMs to engage in planning, reflection, and exhibit basic reasoning skills. Now we can answer this question. What is an AI agent? An AI agent is a system that can perceive its environment, collect data, make decisions, and take actions. Remember that AI agents can perceive their environment through sensors such as cameras or microphones. A text prompt is not the only way for it to receive inputs. Now, let's go over an agent workflow to understand how it functions. Here is a prompt template or instructions. You are a friendly agent that can answer questions about dates and current weather. If user asks about dates, use the calendar tool. If user asks about weather, use the weather tool. Ask user for additional information where necessary. Configuring instructions and list of available tools and their interfaces are part of agent setup process. The user prompt or query is, what is the weather like right now? Note that there is no geographic location or city specified in this query, and we will see how this is dealt with. At this point, agent prepares overall prompt using the instructions, user query, and any additional information it deems necessary, which is then sent to the large language model. LLM reasons and responds that the weather tool must be used to get weather information, and for that we need to know the city name because the weather tool interface expects that. It poses a question, what is the city for which you want to know the weather? And this question is posed to the user by the agent now. User responds with the city name, Chicago. At this point, the agent may choose to store this information in memory. That is, user is interested in weather in Chicago. And then it invokes the weather tool with city as the parameter. Note that the interface and protocol for invoking the tool was made available to the agent during its setup. The tool responds with temperature value of 67 degrees Fahrenheit. Response from the tool is received by the agent and it passes on this information to the LLM to formulate a response for the end user. LLM responds with, hi there, current weather in Chicago is pleasant 67 degrees Fahrenheit, which is typical for this time of the year. And this response is returned to the end user. So that was the overall agent flow. Note that in this process, LLM is not really aware that an orchestrator is using it as a part of a larger framework. It simply works with the instructions and prompts passed to it. Therefore, it is very important that agent is provided with clear instructions via the prompt template and list of available tools, their purpose, and their interfaces. Agent will use all of this to orchestrate the flow. It is a good idea to provide the agent with examples. These are typical use cases for the agent to refer to. These examples could also serve as few-shot learning for LLMs. An agent can invoke other agents, so specialized agents can work in tandem towards a common goal. So, what is the difference between automation and AI agents? Automation typically follows predefined rules, while AI agents can learn and adapt to their environment, making them more flexible and capable of handling complex tasks. Agents may invoke LLMs several times before it responds to the end user. It may do this for additional planning, reasoning, or just to refine the response received from the LLM. So that was an overview of AI agent architecture and workflow. Model Context Protocol. Let's try to understand why we need MCP. Earlier, we just had LLMs to which we sent an input and got an output. Simple. Then we had agents which act as orchestrator and provide some flow control and use LLM for reasoning. However, that is not much of an improvement. Agents should be able to perform actions, which is done by using tools. So, agents perform orchestration, use LLMs for reasoning and language, and tools for actions. This is good, but if you want to add another tool or modify the tool interface, you will have to update the agent. In other words, the tools are closely tied to the agent. We need these to be loosely coupled. So we add a layer called MCP or Model Context Protocol, which hides away the complexities of tools. You can add, update, or remove tools behind the MCP server. Agent simply queries the MCP server to find available tools, their interface schema, and invokes these tools as necessary via MCP. This provides some sort of plug-and-play architecture for tools. Using this simple abstraction, you can make agents powerful and very easy to develop. MCP servers can provide access to not just tools, but prompts and resources too. Prompts are predefined templates and resources are static or dynamic data such as files. However, we will discuss only tools here. Our user prompt is what products are available. Our agent using the MCP client queries the MCP server what are the available tools. MCP server returns list of available tools. In this case, get product list and get order details. Now the agent sends the user prompt and list of available tools to the LLM. LLM reasons and responds with name of the tool that must be invoked. The agent then sends a request to the MCP server to invoke the get product list tool. MCP server invokes this tool, get product list. The tool then returns list of products, which the MCP server returns to the agent, which is then forwarded to the large language model. LLM then formulates a response. Here are the list of products. And that's the final output that the agent returns to the user. Here are the list of products. So that is how MCP works. Vector databases. Why do we need vector databases? Let's understand this with an example. Here is an image of a dog. And here are two different images of dogs. Both these images are similar. What about these two images? They are different. One is image of a dog and other of an elephant. As humans, we can easily tell how similar or different two images are. This is difficult for machines or databases to do. Traditional databases are not equipped to handle this. This is where vector databases come in. They give us a way to search by meaning rather than just a text or a simple number match. For this to work, source data, in this case images, is converted to vector embeddings which are then stored in vector databases and indexed. This allows similarity search to be performed on them. Remember that any kind of source data can be represented as vectors and not just images. For example, words, which is useful in natural language processing. Here's a diagram that shows how vectorization is done. Source data is fed into an embedding model to convert it into vector embeddings that are then stored in a vector database, where they are indexed and available for search. So vector embeddings are simply an array of numbers. But why do we do this conversion of data to vectors? That's because machines can work with numbers easily. And what do these numbers in vectors represent? They represent various dimensions of the source data. As an example, in images, dimensionality refers to the multitude of features, color, texture, shape, etc. So each dimension corresponds to a specific feature. However, dealing with high dimensional data comes with challenges in terms of storage and computational efficiency. Therefore, to make high dimensional data more manageable, dimensionality reduction techniques may be adopted. These techniques preserve the essential information while reducing the number of dimensions. Vector embeddings are typically indexed inside a vector database to enable efficient storage and retrieval. Vector embeddings are organized in a data structure that supports efficient indexing. Common structures include tree-based or hash-based structures. The goal is to group similar vectors together to minimize the search space during similarity searches. So, how is similarity search performed? This is done by finding distance between vectors. Vector embeddings that represent similar data will be closer to each other in the vector space. Vector representation of a cat will be closer to that of a dog compared to that of an elephant. Similarly, vector representation of a king will be closer to that of a queen compared to that of a tree. Metrics like Euclidean distance or cosine similarity can be used to measure the distance between vectors. Here are some examples of embedding models and vector databases. OpenAI, Hugging Face, Cohere provide us embedding models, and Milvus, ChromaDB, and Pinecone are examples of vector databases. Here's a list of popular vector databases and some traditional databases that also support vector search.